Hello students, and welcome again to Topic 3 of Alternative and Renewable Energy Sources. We will continue to cover solar energy fundamentals. This is the last part, Part 3 of Solar Energy Fundamentals, and a very important part. In each part, we will do an activity. The activity is recorded, and you are to work the activity along with the recording. We will again go over some terminology. Solar window is the area of the sky that the sun traverses between summer and winter solstice. Here is a very descriptive visual. Peak sun is defined here. Peak sun is 1,000 watts per meter squared. It is an important quantity because solar cells or modules are rated at a solar intensity of 1,000 watts per meter squared. This is another important terminology or quantity. That is peak sun hours, abbreviated capital PSH. Here is shown what might be the intensity of the sun over a day. It looks like an upside down parabola. If we can calculate the area under the parabola and represent that area as a rectangle with a peak sun, 1,000 watts per meter squared, it will extend over so many hours of the day. It's important to note that the area of the curve under that parabola is equal to the area of the rectangle. The number of hours of the day, which is sun intensity, is represented by 1,000 watts per meter squared, is referred to as peak sun hours. This is a quantity, peak sun hours, that is used to represent the solar intensity in tables. We will cover this more later. Here's a rather formal definition of peak sun hours. Peak sun hours is the equivalent number of hours per day when the sun radiation averages 1,000 watts per meter squared. Let's look at an example. If during the day we have a solar intensity of 500 watts per meter squared for 4 hours, and a solar intensity of 250 watts per meter squared for 6 hours, we can calculate the number of peak sun hours. 500 watts per meter squared times 4 hours would be equivalent to 2,000 watt hours, or 2 peak sun hours. 250 watts per meter squared times 6 hours is equal to 1,500 watt hours, or 1.5 peak sun hours. Therefore, in this example, there are a total of 3.5 peak sun hours. Tilt angle of an array is shown here. It's the angle that exists between the horizontal and the angle at which its surface is tilted. In this case, the surface is the solar module or an array. The angle that the surface of the module makes with respect to south is referred to as the azimuth angle of the array. Here is shown the solar module and the angle that its face makes with respect to south. The incident angle to a surface or array is the angle that the direct beam solar radiation makes with a perpendicular to the surface. Magnetic south normally is not true south. There is an angle that exists between magnetic south and true south, which is called the magnetic declination. Here's an example of a magnetic declination equal to plus 5 degrees. Here is shown what the magnetic declination is at different locations in the continental United States. This is a time series of the magnetic declination and how it changes over a period of time. This is a typical solar radiation table. This one is for Dayton, Ohio. It gives us different conditions for the tilt angle of the surface and also single and double axis tracking. Single axis tracking means that the surface follows the sun throughout the day. Double axis tracking means that the surface not only follows the sun throughout the day, but also throughout the year. It should be noted that the fixed array and the single axis tracking, there are 3 different rows. The center row lists the peak sun hours average per day for that month for a surface with a tilt angle equal to the latitude. Then there are 2 other rows for the tilt angle of the surface or array, one for the tilt angle equal to the latitude minus 15 degrees and one for the tilt angle to the latitude plus 15 degrees. If there are any questions, please post them on the eLearn Help discussion.